Hi everyone, my name is Varun Gautam and I'm a specialist solutions architect in the in-memory team at AWS. Today I will be discussing a new feature of ElastiCache Valkey 8.1. This short video is for audience who uses ElastiCache for Redis or Valkey. This presentation outlines a new feature in ElastiCache 8.1 called Bloom Filters. Bloom Filters was introduced in Valkey OSS 8.0 and later in ElastiCache for Valkey 8.1. This slide covers the fundamental characteristics that make Bloom filters unique and valuable. Let me walk through each point. First, Bloom filters are space efficient because they don't store the actual data items, just bits in a bit array. Compared to conventional hash tables that store key value pairs, Bloom filters can achieve 90% plus memory savings for membership testing. The time complexity is of order k, where k is the number of hash functions, typically 7 to 10. This means operations are extremely fast and predictable regardless of how many items you've stored, whether it's 1000 or 1 million items. One key limitation is that you cannot remove elements once added. This is by design. The bit array structure doesn't allow safe deletion without potentially affecting other items that share the same bit positions. The probabilistic nature is crucial to understand. When you query a Bloom filter, you get one of the two answers: definitely not in the set or probably in the set. The definitely not is 100% accurate. This is the no false negatives guarantee. However, probably yes might be wrong due to hash collisions from other items setting the same bits. This trade-off between space efficiency and perfect accuracy is what makes Bloom filters so powerful for high-volume screening applications where occasional false positives are acceptable, but missing actual items would be problematic. So these use cases demonstrate the power of Bloom filters for answering "have I seen this before" questions at massive scale with minimal latency. For advertisement deduplication, imagine serving millions of ads daily. Instead of querying a database every time to check if a user has seen an ad or not, you can get an answer instantly from a Bloom filter. If it says definitely not shown, you can serve the ad immediately. If it says probably shown, you might skip that ad or do a quick database verification. In case of fraud detection, Bloom filters excel at first line screening. You can filter a stolen card number and instantly screen transactions. A definitely not flagged results lets the transaction proceed immediately, while probably flagged triggers additional security checks. This dramatically reduces database load while maintaining security. For spam and content filtering, Bloom filters can store millions of malicious URLs or spam email addresses in just a few megabytes. When a user clicks a link and receives an email, you get instant screening results. The false positive rate can be tuned based on your tolerance, maybe 0.1% for general filtering and 0.01% for crucial security applications. Username availability checking is perfect for Bloom filters because the user experience benefits from instant feedback. When someone types a username, you can immediately tell them if it's definitely available or potentially taken. Then verify with the database only for potentially taken cases. This reduces database queries by 90% plus during peak registration periods. The common thread is using Bloom filters as a fast pre-filter before expensive operations, dramatically improving performance and user experience. So these are the core commands that you'll see when working with the Bloom filters in Valkey. Let me highlight the key operation patterns. bf.add and bf.exists are the bread or butter operations for single items. These are of order k operations that execute in microseconds. bf.add returns 1 if the item was newly added, or 0 if the item is already present or appears to be due to false positives. The bulk operation bf.madd and bf.mexists are crucial for performance when dealing with multiple items. Instead of making separate network calls for each item, you can batch them together. This is especially important in high throughput scenarios where network latency matters more than processing time. bf.reserve is essential for production deployments. While you can let filters auto-create with defaults, explicitly reserving with your expected capacity and error rate is much more efficient. For example, bf.reserve usernames 0.001 1 million creates a filter for 1 million usernames with 0.1% false positive rate. bf.insert is the most flexible command. It can create the filter if it doesn't exist and allows you to specify advanced properties like custom seeds or validation parameters. It's particularly useful in application startup scenarios. bf.info is your monitoring and debugging tool. It shows capacity, current size, number of items, actual error rate, and scaling information. Use this to monitor filter health and plan capacity. bf.card gives you the estimated count of unique items added. Note this is an estimate because Bloom filters don't store the actual items, just bit patterns. The key is choosing the right command for your case: bulk operations for performance, reserve for production setup, and info for monitoring. So bf.reserve is essential for production deployments. While you can let filter auto create with defaults, explicitly reserving with your expected capacity and error rate is much more efficient. For example, bf.reserve usernames 0.001 1 million creates a filter for 1 million username with 0.1% false positive rate. So this particular command creates a new Bloom filter called new underscore customers with capacity of 1000 times before scaling, and then error rate 0.01 1% false positive rate. Initial items will be added as customer A and customer B, and integer 1 will be returned when the items are added. The Bloom object is primary data structure created with the Bloom filter creation command. It offers two operational modes: non-scaling, which enforces a fixed capacity and returns an error when it's full, and scaling, which automatically grows by adding new subfilters when capacity is exceeded. Subfilters are an inner structure within the Bloom object that have a certain capacity or number of items it can hold. You can set the capacity for the first subfilter, and then in scaling mode, the expansion rate determines how the capacity of newly created subfilter grows. You can also configure what false positive rate is acceptable for your workload, which determines how often such false positive occur. Making your Bloom filter more accurate with fewer false positives requires more memory usage, though only marginally. Because scalable Bloom filters can grow and expand over time as items are populated, individual Bloom objects are susceptible to experiencing memory usage errors when attempting to scale out. For example, you can address this in two ways. First, before implementation, check your capacity requirements and use bf.insert command with the validate scale to option to make sure you plan filter capacity, along with other configured properties. This fits within the 128 megabyte memory limit per object. This helps prevent insertion errors later due to memory constraints while maintaining your desired accuracy. Second, for existing filters, use the bf.info command to find out the maximum capacity that your scalable Bloom filters can expand to hold. This helps plan for your application requirements before hitting memory limits. In this case, the filter can hold 26,214,300 items after scaling out until the memory limit. Have a time complexity of order k, where k is the number of hash functions. Because they operate on a single item, for Bloom commands operating on n items such as bf.insert, bf.madd, and bf.mexits, the complexity becomes of order n into k. Commands like bf.card, bf.info, bf.reserve, and bf.insert without items operate in constant time. In scalable Bloom filters, each scale out introduces a new subfilter, each requiring additional hash functions checks for the commands operating on it with items. As the filter scales, the false positive rate of the new subfilter becomes stricter by default, which can increase the number of hash functions. Therefore, when a Bloom filter scales out several times, such as more than 100 times, the performance can begin to degrade. To avoid excessive scale-outs and their performance costs, it's recommended to choose a suitable starting capacity and expansion rate based on expected workload. For example, to store 10 million items, we can use a starting capacity of 100,000 with expansion rate 1, resulting 100 subfilters after 99 scale outs. However, we can avoid excessive scale-outs with two approaches. One would be to use a high expansion rate of 2 to achieve 12.7 million items with just 7 subfilters. Other would be to use a higher starting capacity of 1 million to achieve 10 million items with just 10 subfilters. So trade-offs, basically higher expansion rate and fewer subfilters. So fewer hash checks per operations, but wastes memory if actual data is much smaller than capacity. And then lower expansion rate, more subfilters, more hash checks per operation. So slower bf.exist and bf.add, but it uses memory efficiently. The Bloom filter solution in ElastiCache uses the Valkey Bloom module from Valkey open source project and therefore is fully compatible with the open source module. And it's API compatible with Bloom filter command syntax for Valkey client libraries, including Valkey Pi, Valkey Java, and Valkey Go, as well as equivalent Redis libraries. Bloom filters are a powerful addition to the ElastiCache toolkit, enabling fast, scalable, and space-efficient membership testing across a wide range of applications. As shown in the real-world examples of ad deduplication and fraud detection, Bloom filters delivers dramatic memory savings often over 90%, by trading off a small configurable rate of false positives, all without compromising performance. With native support in ElastiCache version 8.1 for Valkey and full compatibility with open source Valkey clients, adopting Bloom filters requires minimal effort and offers immediate value. Bloom filters are available today in ElastiCache version 8.1 for Valkey in all regions and for both node-based and serverless offerings. To learn more about Bloom filters on ElastiCache for Valkey, refer to ElastiCache documentation. For the full documentation and list of supported commands, see the Bloom filter documentation on valkey.io. For getting started on Amazon ElastiCache, please scan the QR code to access various learning resources, use cases, and prescriptive guidance. Thank you for watching this video.